In this lecture, I want to talk about something called implicit differentiation. So first, let's try to understand what we mean by implicit. So if we consider a function of the form y equals x cubed plus 1, this is explicit in the sense that we know exactly how y depends on x. You know, we change x, we can just get values for y. It might be easier to understand explicit in terms of something that's not. So let's think about something like this. Y to the fourth plus xy equals x cubed minus x plus 2. So let me just sketch a quick graph of the curve that is traced out. So basically what we're looking for are all points x, y that satisfy this equation. All right, so you would end up with something we kind of come in, dip down, come around, and kind of come back like this. It's not completely symmetric, but and so this is the x, y axis. This is what we would have something like this. So each point on this graph satisfies this. So for example, the point 1, 1, we can show that's actually on this curve by showing that it satisfies this equation. So for example, if we put in 1 for y and 1 for x, well 1 to the fourth is 1 plus 1 times 1, and here's the question, does that equal 1 cubed, which is 1, minus 1 plus 2? Well, that is 2. That's 0 plus 2 is 2. So yes, this point, 1, 1, is on this curve. But notice it would be difficult, maybe impossible, to solve for y like this, right? Just to have y equals and have everything in terms of x on the other side. So right here we can see it would get very difficult, right? Like how do we get this x out of here? We could factor a y out, but we'd still be left with y cubed plus x. So trying to get y basically by itself to the first power on one side, and then everything else in terms of x and constants on the other, it would be difficult, if not impossible, to do that in this case. However, that doesn't mean that y doesn't depend on x, right? As we could change x, then y would have to change accordingly in order to maintain this equality, right? So it does depend on x, but it's certainly not a function. We see that right here. The y-axis intersects in two places, so we know it's not a function. But we could still ask the question, what is the equation of the tangent line? So let's say, I don't know, maybe like right here is the point 1, 1. We could still want to know maybe the equation of the tangent line. How is this, or the slope of the tangent line? What's the instantaneous rate of change of this curve at 1, 1? Right? How is it changing with respect to x and y? All right. So that's why we care about being able to find derivatives of things like this. So that's what we're going to look at in this lecture: is how do we find such derivatives. So I'm going to start with an example. A simpler example than the one that we were just looking at there. We'll come back to that one at the end, but let's think about something like x squared plus y squared equals 1. So you should recognize that as the unit circle, right? So it's a circle centered at 0 with radius of 1. So something sort of like that, all right? Now suppose we also know that 1, 1 is on the graph of this, and suppose we wanted to know the equation of the tangent line there. All right, it would actually keep going, right? All right, so let's say we wanted to know the equation. We know that 1, 1 is on the graph because I put in 1 for x. So this is the point 1, 1. If I put in 1 for x and 1 for y, whoops, actually 1, 1 is not on the graph, is it? How embarrassing. It'd actually be 1 over the square root of 2, 1 over the square root of 2. Now I could also just change this to 2, which would make our lives a little bit easier if we wanted to find the equation. But nonetheless, we could find, for any of these points, we could find the equation of the tangent line. We just have to make sure they try to satisfy our equation, right? So, anyways, let's take a look at how we would find the slope of the tangent line, which would be the derivative. So, clearly we would take the derivative with respect to x of x squared plus y squared equals the derivative with respect to x of 1. Now we know that the derivative of the sum is the sum of the derivatives, so I can rewrite this as the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals, and we know the derivative of the constant is 0. Now this is straightforward. That's about as simple as they come in terms of the power rule. The question is, how do we evaluate something like that? Because in other words, y is some function of x, but we don't know what it is, right? So let's say y is some function of x, all right? And this is not uncommon, that we're trying to find, we don't know explicitly what y is in terms of x, but we can still find the derivative with respect to x. So the answer is not 2y, all right? Because there's a function in there, right, that's being squared, and we don't know what that function is. So this is kind of notationally maybe kind of a way to think of how we could approach this. Because what I could do is I could say, well, the derivative with respect to x of y squared would be like the derivative, I mean, it's equivalent to saying the derivative with respect to x of f of x squared, all right? And we can see here that the generalized power rule or the chain rule would work here, right? So I have this, the outside function is the x squared function, and the inside function is just f of x. So to find that derivative, I multiply by the 2, and then I make that into a 1, which I don't need to write. And I still have this, but then the chain rule says I have to multiply by the derivative of the inside function. All right? So if we think about that in terms of y, we would get 2y times y prime. So it's important to see where this y prime comes from. It's a result of the chain rule, because we have this function of x being squared. Whether you call it y or f of x doesn't really matter, but the point is it's being squared. So we have a composition of functions. We have some function being squared. So we have to first, the outside gives us the 2y, but the inside we have to multiply by y prime. We don't know what it is, but we just write y prime because we know we have to multiply by the derivative of the inside function. So we're going to add to this our 2y times y prime, and we have that equal to 0. Now let's subtract 2x from both sides, so I end up with 2y times y prime equals negative 2x, and then I can divide both sides by 2y. So notice what I'm doing is I'm solving for y prime. I'm solving for my derivative. I want to find, so in other words, even though I can't necessarily get an explicit function of x for y, I could get an explicit function for y prime. Although, notice it's not going to be in terms of only x. So the 2's divide here, right, and I'm just left with negative x over y. All right. So here I can solve for y prime even if I can't solve for y. Actually, it wouldn't be too hard in this case, but in the case that we started with, trying to solve for y is just about impossible. Actually, off the top of my head, I can't think of a way to solve for y. But we could still solve for y prime. That's what implicit differentiation allows us to do, is solve for y prime even if we can't solve for y. So notice then, so y prime evaluated at 1, 1 would give us negative 1 over 1, although that's not actually our point, right? Our point is 1 over square root of 2, or 1 over square root of 2. That still works though, right? Because negative 1 over square root of 2 over 1 over the square root of 2 still gives us negative 1. And if you look at that makes sense, right? It's a negative slope. It looks like it's going to hit the x-axis at about the same place as the y-axis, right? In terms, if this was, well, let's say, if this were 2, then that would also be 2, right? There's a slope of negative 1 there. So if we wanted to find the equation, when you now know the slope, it would just be y minus 1 over square root of 2 equals negative 1 times x minus 1 over the square root of 2. Not pretty, but that is the equation of this line. Okay, so that's kind of the idea. It's this idea right here that we're going to take using the chain rule is how we solve for y prime. Okay, or at least we find the y prime and then we plug it back into our equation and we solve. Let's just see another example of that, because that was just kind of an introduction. So let's say we wanted to find y prime for the curve e to the xy equals x plus y. Again, this is the curve that is traced out for all values of x and y that satisfy this equation. So we would need to take the derivative with respect to x of e to the xy. Also want to point this as another occasion where it would be difficult, if not impossible, to solve for y explicitly. And then on the other side, we take the derivative with respect to x of x plus y. All right, so here we need to remember, how do we take the derivative of e to some function of x? Well, the derivative with respect to x of e to some function of x is f prime of x times e to the f of x. So what that says about this is that I'm going to basically take xy prime e to the xy. So that's what's going to happen on the left side. On the right side, I'm going to, the derivative of the sum is the sum of the derivatives, so I can rewrite this derivative with respect to x of x plus the derivative with respect to x of y. So what about this? How are we going to deal with this? Well, one way to think of this is that the derivative with respect to x of y, it's just going to be y prime. But we can also think about it in terms of the power rule. So we can think of this as y to the first power, right? So if I use the generalized power rule, when I take the derivative of this, I bring the 1 down out front, still have this in the middle, to the 0 power times the derivative of the inside function, which is y prime. All right? But anything to the 0 power is 1, and 1 times 1 is 1. So this is just going to be y prime. I think that throws students a little bit, because we see y like y squared or e to the y or sine of y. That's a little bit different. When you just see a y by itself, it can be, it's slightly different. But this is a way to think of it. But probably the simplest way to think of it is when I'm taking the derivative with respect to x of y, that's just going to be y prime. Okay, so this side's easy, right? Derivative of x with respect to x is 1, and that's just going to be y prime. Let's take a look at this, because here we have x times y, so we are going to need the product rule. So over here then, so if I take the derivative, let's say we're going to take the derivative of x times y plus x times the derivative of y. All right? So the derivative of x is 1 times y plus x times the derivative of y. Well, we just talked about what that would be, so that's xy prime. So this whole thing times e to the xy. Now our goal is to solve for y prime. In the last example, it was a little bit simpler because there was only one y prime. So we bring the 2x over, divide by 2y, and we're done. Here, we're going to have to group all of our y primes on one side here, factor the y prime out, and then solve. All right. So let's see. The first thing that I think that would help us here is to distribute this, so we can get this one with a y prime away from this one that doesn't have it. Right. So if I distribute here, I'm going to have y e to the xy plus xy prime e to the xy equals 1 plus y prime. Now, let's try to get everything that has a y prime in it on one side. So I will take this and bring it over here. And let's get everything that doesn't have a y prime in it onto the other side. All right, so I will end up with xy prime e to the xy minus y prime. Yeah, y prime, not y to the first. Okay, because I subtracted that from both sides. And then that's going to equal 1, and I'm subtracting this from both sides, so 1 minus y e to the xy. Now here I need to factor out the y prime. So if I take a y prime out, I'm left with x e to the xy minus 1. equals 1 minus y e to the xy. So it's getting a little messy, but don't worry about that. I'm almost there. Now I just need to divide by this on both sides to solve for y prime. So y prime would equal 1 minus y e to the xy over, and now remember I'm dividing by this, so over x e to the xy minus 1. And notice just, we expect a little bit of symmetry to be going on here, right? Because this looks like this, except they're switched, and I have a y instead of an x. But nonetheless, the point is this is y prime, and that's what I was looking for. I wanted to find y prime. So again, I just want to point out, for one, even though we couldn't solve for y here, we can find an explicit expression for y prime. But more often than not, that explicit expression is going to include both x and y. So if I wanted to find the slope of the tangent line, I would need both x and y, right? So first, of course, I would have to find, this point would have to be on the curve first. And it's not entirely obvious what values of x and y would make that true. But given that the point is on the curve, then we can plug it in here and find the slope of the tangent line at that point. All right, then, let's go back to the one that we started with. So we have this curve here, and I do want to find the equation of the tangent line at the point 1, 1. We've already verified that 1, 1 is on the curve, but what we need to do with this is we need to find y prime. Okay, so let me rewrite it up here. We have y to the 4th plus xy equals x cubed minus x plus 2. All right, so we're going to take the derivative with respect to x of both sides. Y to the 4th plus xy equals, and I'm going to just do this. This is going to make a little bit more work, but this side is all just in terms of x or constants. So the derivative of x cubed is 3x squared. Derivative of that is going to be minus 1. Derivative of 2 is 0. So here, I need to take the derivative of y to the 4th. All right. So that's going to be 4y cubed times y prime. Again, you can kind of think of the outside function as being to the 4th, and so that's going to be 4y cubed. But I have this y in here that is a function of x, and by the chain rule, I have to multiply by its derivative. Here, we've already done this one, so we can do it again, but you know we're going to need the product rule in order to figure that out. Although we've already done it, so let's not kill ourselves doing it again. It was right here. We did xy prime, and we found, well, here it is, xy prime, and we found it to be this. So I'm just going to go ahead and write that again. So that's 1 times y, so that's just going to be y plus x y prime by the product rule. And that equals 3x squared minus 1. So again, we need to collect these on one side and then factor the y prime out so we can solve for y prime. So that means I need to get this y over here by subtraction. So I'm going to have 4y cubed times y prime plus x y prime equals 3x squared minus 1 and minus y, because I subtracted it off of that side. Now here I can factor out the y prime. I'm left with 4y cubed plus x equals 3x squared minus 1 minus y. And then I divide both sides by the 4y cubed plus x. All right, and that leaves me, this is, well, so if we divide those out, this is y prime. Now, remember, in this case, I actually want to find the slope of the tangent line at 1, 1. So then y prime at 1, 1, I'm putting 1 for x, so I get 3 minus 1, putting in 1 for y. 4, I'm putting in 1 for y, so that's going to be 4 times 1 cubed, which is 4, plus, I'm putting in 1 for x. So 3 minus 1 is 1, and 4 plus 1 is 5. So that is the slope of the tangent line. We'll see how good of a job I did. Not a very good job of sketching this, right? Because here it looks like the slope of the tangent line would be negative, but we actually found it to be positive. So my sketch isn't very good, but it does look sort of like that. Anyways, we want the equation of the tangent line. So we know that 1, 1 is on the curve. We know that's the slope of the tangent line at that point. This is my point of tangency, so I have y minus 1 equals 1/5 x minus 1. So that is the big idea with implicit differentiation, is that while we can't solve for y explicitly, we can find an expression for y prime in terms of x and y, and we can use that to determine how a graph is changing at a specific point with respect to x and y. We can find the equations of tangent lines to these types of curves as well.